recording this so that it's available for you guys to see on your own time. If you have any like kind of troubling aspects about the lecture. So today, the plan is to cover the labor-leisure consumption model. I'm going to talk about that, and then we're going to do extra problem set 4, and we'll go over how to approach the problems, and as well as like reasoning behind why we do certain things. I know that when it comes to like this new material, especially with, I keep kind of honing in on this, but substitution and income effect, like a lot of it is very conceptual, and so you guys can kind of get lost. And I know that Monday's lecture was maybe not the most clear because there was no application of the concepts, and so you guys maybe are kind of just wondering like, well, what do we do now? So we're gonna definitely go over a ton of problems today, and we'll try to get a lot of practice to prepare you guys for next midterm. All right, so what I want to talk about and what I wasn't able to get to last lecture is the labor supply model. So labor supply, and with labor supply, there's actually going to be a few, or actually quite a few variables that you're going to want to be familiar with, that have to do with the budget constraint that we're working with. And so before I kind of get started with labor supply, I kind of want to talk about what it is at a high level. So essentially, in our day-to-day lives, right, we have a certain number of hours that we can work, that we have available to allocate between work and relaxation. And so the thing about when you work is you make a lot of money, but that's time that you're not able to just relax and enjoy your money. And so there's a certain trade-off that you have to make between working and relaxing. And so obviously when you're relaxing, that is like an hour of wage that you could have been making. And so that's kind of the overview of labor supply. And you'll see how it looks like on a budget constraint, what exactly I mean by that. So I want to introduce some variables. So L is hours of labor a week. We say that W is equal to the wage per hour. We say that W times L is the wage per week, right? Because if you just multiply the wage per hour by the number of hours that you work, that's going to be the total amount of money that you're earning in a week. We're going to say that M is going to be equal to non-wage income. So if you think about what this is, this might be like unemployment money. This might be, I don't know, allowance from your parents. This is basically just money that you get without having to work at all, right? So it's like a starting point. So we say that WL plus M, that's going to be equal to your total income, or your total income per week. C is equal to consumption per week. P is equal to the price of consumption. Bless you, Tim. And so one of the unique things about the price of consumption in this model is that because we just define consumption as being consumption on everything else, right? Similar to, if you guys remember that one taxi problem that I presented, I believe 2 lectures ago, that's going to make it so that consumption is what we call a composite good, meaning that the price is always going to be set equal to 1. And so this will always be true unless it's stated otherwise. But I really have never seen problems in which the price is not 1. So I would just remember that P is always going to be set equal to 1 in these problems. And there's going to be a few more variables. L bar is equal to the maximum hours available. And so L bar is basically the cap at how many hours a week that you can work or relax. So if you think about it, in a week, we have what, 24 times 7 is 168 hours a week, right? So that's kind of like the natural cap on how much you can allocate between working and relaxing. We won't always set it at 168, but that's kind of the intuition behind what the maximum hours per week is. And then one last variable that I want you guys to be familiar with, and I'm sorry that I'm squeezing it right at the bottom, but R is going to be hours of recreation, right? And R can also be considered leisure. So leisure labor, you'll hear that a lot, but essentially what this means is the amount of hours you spend in which you're just kind of enjoying your time instead of working, right? And so through this labor leisure model, with all of these variables that we've constructed, we're going to create a budget constraint. We're going to create a budget constraint that we'll be ultimately working with. And what this looks like is P times C is equal to M plus WL, right? And so this is kind of like the original form of this budget constraint. You're going to see how with a few different rearrangements of variables, we're going to be able to turn this into something that is going to be a little bit easier to work with. And so the way that we do that is by recognizing that L bar is equal to L plus R, meaning that the total number of hours that we have available is equal to the number of hours that we work plus the number of hours that we just relax. And so you notice that we have L in this equation. And so what we do is we kind of just write this in terms of the other variables, so that L is equal to L bar minus R. And so when we substitute this in to our equation, we get P C is equal to M plus W L bar minus R, right? This turns into PC is equal to M plus W L bar minus WR. And so our final form of this budget constraint is PC plus WR is equal to M plus WL bar. And I think that the best way about understanding what this budget constraint means is to actually kind of say it out in words. So W is just the wage. That's like the wage per hour that you're making. That's a good question. And so what I want to say about this budget constraint, and I think that the best way of understanding it, right, is to kind of just read out what it means in words. So this is essentially saying that the amount of money that you consume, or I guess the amount of consumption that you consume, right, where you multiply the amount of consumption times the price, which is going to be 1, right, plus the amount of money that we give up by relaxing. So the reason why we take this into account is because we can kind of think about that as like an opportunity cost of relaxation, right? Where when you decide to relax, that is money that you're foregoing, right? And so we say that this total, the amount that we spend on consumption and the amount that we give up by relaxing, is equal to our total income available to us per week, right? And so hopefully you guys can kind of see like what I mean by that. The constraint at the top is PC equals M plus WL. So the wage times the amount of hours that you work. So this is a W. Okay. Here, maybe I'll try to make it a little bit more obvious, right? So this is going to be the budget constraint that we want to be familiar with. And so hopefully you guys are able to kind of do that same exact reasoning in words of what this means. And I think through that, you'll get a very like better understanding of what this budget constraint actually is representing, right? And so now that we kind of have like established the variables that we're going to be using, as well as the budget constraint that's going to be applicable to this kind of model, let's draw this out, right? Because like any other budget constraint, it can be drawn out. So let's keep in mind that the budget constraint is PC plus WR equals M plus W L bar, right? And we want to draw this out. So let's say that we are, here, that's actually not very straight. Let's say that we have a two-dimensional axis like this, where R is right here, and C is right here. So we got recreation and we got consumption, the two goods that we're going to be kind of deciding between. So just to kind of make it apparent as to why these are our axes, the utility functions for these are going to be in terms of R and C, meaning that these are the kind of goods that are going to be providing us utility, right? And so when we draw something like this, we want to think about, right, the different kinds of axes that we have. And so we want to assume, right, we want to look at, say, this axis first and say, when I'm here, what does that tell us about how much we're able to consume, right? Well, if you set R equal to 0, that leaves us with P times C is equal to M plus W L bar. And so that gives us that C is equal to M plus W L bar over P, where P will typically be 1, right? And so because of this, now we're going to be thinking, well, if we're consuming only leisure, meaning that every hour that we have available to us is spent on leisure, right? How is that going to be positioned on this graph, right? And something that I want to note is that this ultimate level of R is equal to L bar, right? So if you remember, L bar is equal to L plus R. And so if we're working 0 hours, this becomes 0 plus R, meaning that L bar is equal to R, right? So hopefully you guys can kind of see what I mean by that by substituting in this L bar, right? And an interesting thing that you guys want to be familiar with is the fact that because L bar is equal to L plus R, right? Basically everything in between here is going to be L plus R. And so what I mean by that is, say that we're currently consuming this amount, right? Say that we're currently consuming something like here, where this is the level of kind of labor that we're going to be doing, right? Everything here, actually it should not be an L bar. That should just be an L, right? Everything to the left of this point right here is going to be the amount that we work, and everything to the right is going to be the amount that we relax, right? So this right here is work, and this right here is leisure, right? And remember, leisure and recreation are kind of interchangeable, right? So that's something that you guys want to definitely be aware of, right? When you're looking at this model. And I think I might have gotten it actually switched up. So let's just draw that out first, and then we'll kind of check back with our work when we get there. But so kind of take that with a grain of salt right there, and let's just kind of see where we go from here. But the next intercept that I want to get to, right, is basically seeing where I'm going to be at when I'm only consuming leisure, right? And so basically what we can kind of see is that when L bar is equal to R, I get PC plus WR is equal to M plus WR, right? Because L bar turns into R. And so I can kind of just cancel out from both sides. And I get PC is equal to M. So that C is equal to M over P. And what this level of consumption is basically, right, our non-wage income divided by how much each unit of consumption costs, right? And so that's going to make sense because, right, if you think about what this says is that even though we're not working at all, we still have some sort of non-wage income that we received that's going to allow us to consume positive units of C, right? And so what essentially is going to happen is we form a little king point right here where we get a straight line connection from M over P, comma, so this point right here is L bar, comma M over P, right? And we're gonna get a connection between here and here, right? And so where this king point is based on what the level of M we're given in the problem. So it could very well be that M is just 0 and we have no non-wage income. And so what happens in that scenario is that basically we would get something that connects all the way down to this axis because our consumption would be 0 if we work 0 hours, right? So hopefully that kind of makes sense to you guys. I do want to kind of explain what I mean by this distinction between which side of this point is leisure and which point is labor. First, I do want to point out what the slope of this is going to be. So the slope of this line is going to be negative W over P, right? And so you guys can kind of think about why it is. And the reason why is because this is the cost of consumption and this is the cost of recreation, right? And we're essentially just finding that ratio, which just happens to be the wage that we could make through an hour of labor. And so that's what we're giving up. And P, right, is what it costs us to consume 1 unit. And so this is going to be the slope of this graph. And so I want to get to this point right here, right? So assume that we're consuming right here, right? That would tell us that we actually consumed, or we actually performed this much amount of labor. So I had it switched up. This much amount of labor and this much amount of recreation. And I'm going to explain to you guys why it is that this space right here is recreation and this space right here is labor, right? So assume that we're starting off at this point right here. That would mean that we're only consuming recreation, right? And so as we move towards this way, right, that means that we're going to consume more consumption. So we're going to be making more money, which means that we have to be increasing our labor. And so as we move along this direction, that's going to imply that our labor is increasing, right? Because in order to get to this point right here at the very top, that means that we're only working and we have no relaxation. So hopefully you guys can kind of see why it is that we've kind of split up our axes between recreation and labor. And hopefully you're able to understand why it is that it's broken up that way. How did you get the point on the C axis? So this point right here, is that what you're referring to? I'm going to assume that's what you're referring to. This point right here is when R is set equal to 0, because this is the point where we're working all of the amount of hours that are available to us, and we're relaxing 0 hours. And so R is going to be equal to 0. And so we get PC is equal to M plus W L bar. And so in order to find the level of C, we just divide through by P. Does that kind of make sense?
Yeah, thank you.
Also, yeah, if there's any questions about anything about this model, I know that it's totally different than the regular P1 x1 plus P2 x2 equals M. So definitely don't be afraid of asking questions about that. I do want to point out some things about this model. So more specifically, I want to point out what happens when we get certain shifts in say like income or say wage. So yeah, let's get into that. So I want to talk about what happens when we get an increase in income. So you can kind of think about these as being like shifters of our budget constraint. When we get an increase in income, you want to think about all of the points that actually contain the variable M, right? And so that's going to be this point and this point, right? And because we know that that's connected by a straight line, we know that essentially when we get an increase in M, that's going to push our budget constraint upwards so that it gets a parallel shift, right? And we know that it's parallel because nothing is affected with regards to wage or prices. And so basically, our numerator is greater in both instances. And so that's going to lead to an increase of our budget constraint through a parallel shift. Now, I want to talk about what happens when we get an increase in wage. So also, I urge you guys to think about which of these points contain any level of wage. And so you notice that this axis right here has wage in the numerator. And so that means that as wage increases, so is this point right here. However, when you look at what this point is right here, there's nothing about wage that is involved, meaning that this point is going to stay right here. And so we get a straight line connection to this king point. And right, this makes sense because as wage increases, you would expect the slope of our budget constraint to also increase and become steeper. And so that's essentially what's happening right here. So to kind of sum up what I just said, an increase in the my God, I stumbled. An increase in the non-wage income is going to lead to a parallel shift outwards, whereas an increase in the wage is going to lead to an increase in the slope, right? And you guys can kind of extrapolate what would happen when M decreases and when W decreases, right? So you can kind of think about that with regards to our original budget constraints, the P1, X1, P2, X2, right? When M increases in that model, we get a shift out. When price changes, right, we get those pivots that we see. So that's essentially what's happening here. And so that's kind of all I wanted to cover about this model. I want to make sure that we have enough time for practice problems. But are there any questions about anything that I just covered? Maybe some things that didn't quite make sense that you'd like answered? All right. It's looking like there's not too many concerns, so I'm just going to assume that you guys understood that fairly well, or at least have a decent understanding of what kind of is going on. I would definitely play around with that, just kind of test to see what happens when certain things are changed, because that'll for sure give you a better understanding of what's going on. Now, as for today's agenda, I know that it's already 1:23, so we have about 25 more minutes, but I wanted to get into extra problem set 4. And I saw that on your guys' Gaucho space, a video for problem set 4 was already posted, so I encourage you guys to watch through that video in order to get a better understanding. But for now, I'm going to ask you guys to go to your extra problem set 4 so that we can kind of work through this together. And I'll give you guys about 20 seconds to do that, 20, 30 seconds. Extra problem set 4. So can I get some thumbs up in the chat when you guys were there? All right. So I'm gonna guess that was enough time for everybody to get there. And so let's kind of just work through it one problem at a time, and we'll see how we feel about each problem. Feel free to stop me if you have any questions, but I'm gonna try to go through this as fast as I can, just so that we have enough time to get through as many problems as possible. So let's look at question number 1, right? We're given a utility function that looks like x1 equals, sorry, a little bit messy, x1 times x2. And actually, x1 is xa and x2 is xb. So I just kind of confused myself. but it should be still the same. So the price of apples used to be 1. So P1 equals 1 to start off with. And the price of bananas used to be 2, right? And income used to be 40. And we're given that the price of apples, which is price of good 1, went from 1 to 5. And so what they're asking for us to do is find the change in the consumption of apples due to this change in price. And so immediately, I think what's going to be helpful for us is to set up a chart that looks something like this so that we can kind of understand where the changes are happening, right? And what specifically the substitution effect for apples is going to be. So this is the main question, is what this slot here is going to be. So the first thing that you're going to want to do, right, is to plot down where the original point is, right? So first, we're going to be able to draw out a budget constraint. So this is going to be 2040, right? So this is the budget constraint that we're going to be working with. And we're going to be able to find an optimal point given this utility function, right? So many of you guys probably already know where the optimal point is going to be just from the income share method. But I like to just solve these problems kind of how I always solve them. So find the MRS. We have DMRS, right? So we can set this equal to the price ratio, which is 1/2, right? Because we're dealing with the original situation. And we get that 2x2 is equal to x1. And so when we plug this into the budget constraint, we get that P1, which is 1, times x1, which is 2x2, plus P2, which is 2, and x2, which is just x2, is equal to 40. And so we get that 4x2 is 40, and so x2 star is equal to 10, right? And so basically that tells us that because x2 is 10, then x1 star is equal to 20. So our point A is going to be at the bundle 2010, okay? And so where that lays on our budget constraint is going to be right here in the middle, just like that. So we've gotten kind of done with point A. Now we want to see like how we're going to be able to figure out the substitution effect for apples. Now, the way that I like to go about these problems is I actually like to solve for point C first, because we're going to use the information from both point A and point C to kind of hone in on point B. And I'm going to show you guys what I mean in just a second. So let's look at point C. So point C. And we know that point C is going to be done the same exact way that we solve point A, right? Except that we're going to be working with a new budget constraint. So nothing is going to change here on the x2 axis. So x1, x2, just to make sure that we're properly labeling. However, we're going to go from being able to afford 40 units of good 1 to now we're going to be able to afford 8 units. So we get a new kind of axes intersection that's going to look like this, right? And so given this information, we still know that our MRS is going to be x2 over x1. That doesn't change because our utility function doesn't change. We know that we had DMRS. And so we're now going to be able to set this equal to 5/2, which is our new price ratio. And we get 5x1 is equal to 2x2. It doesn't really matter which variable you solve for, but I'm just going to solve for x1. And so we get x1 is equal to 2x2 over 5, right? And so when I plug this back into the budget constraint, I'm going to get 5 times 2x2 over 5 plus 2x2 is equal to 40. And so the 5's cancel out, and I actually get that x2 star is going to be equal to 10, right? So our level of x2 actually is going to stay the same, right? But we know that as a result, because the price of good 1 changed, x1 star is now going to be equal to 2 times 10, 20 over 5, which is 4, right? And so we're going to go from the bundle 2010 to the bundle 410, right? And that's going to be our point C. All right, so this is right around here, right? And so we've gotten our point A and our point C. And so now all that's left is to find point B. Now, the reason that I like to find point A and point C first is kind of what I mentioned before. We're going to be able to lock in, right, where our point B is. And so we're going to use some of the information that I gave to you guys in the first lecture, which was that utility at point A is equal to the utility at point B, and that the slope at point C is equal to the slope at point B, right? And so given this information, that tells us that point B is going to be somewhere on this indifference curve, and it's also going to be tangent to this curve right here, which is the new budget constraint, meaning that the slope at point B is going to be equal to 5 over 2, because that's the new slope of the budget constraint, right? And so that tells us that point B is going to be somewhere over here because of the fact that we have DMRS on our curves, so that the slope right here has to be higher than the slope here. Okay, so that already gives us an idea of where point B is going to be. And so because we know that the slope at C is equal to the slope at B, we know that the MRS, right, which is the slope of the indifference curve at any given point, right, so x2 over x1 is going to be equal to 5 over 2, right? And so this step should look familiar because that's what we used to find point C, right? And so now we can get this relationship, 5x1 is equal to 2x2, right? And I'm just going to isolate for x1 again. So x1 is equal to 2x2 over 5, all right? Now, that doesn't quite tell us all the information that we want to know, because we still have to account for the fact that the utility at point A is equal to the utility at point B. However, we have enough information here, right? And that's going to be because of the fact that we know what the bundle is at point A, meaning that we can actually fill in these points, 2010, into our utility function and get an actual value that we're going to set equal to the utility at point B, right? And so what this is actually it's going to be 20 times 10, which is going to be equal to 200. And so that tells us that the utility at point B has to be equal to 200. Is everybody following so far? Are there any questions about that? MU1 over MU2. Yeah, so MU1 is x2 and MU2 is x1. And the number 8 comes from the fact that 40 divided by 5 is 8. So I'm seeing some people that are a little bit lost. And so I'll kind of try to slow it down. So let me kind of just take a step back. Does everybody understand where point A and point C came from? Yeah? Okay, awesome. Now, does everybody understand why I set the MRS equal to 5 over 2 in order to find point B?
I have a question about that.
All right, and make sure that you speak up if you don't, because it's quite all right. This is kind of like a nuanced thing to be able to understand.
Can I ask a question?
All right, I saw one yes. Any other yeses or any other no's?
Can you hear us? I think someone is trying to ask a question.
Okay, so I'm gonna, why did I set it up like that? So I can definitely hear if you put your,
Wait, can you hear us?
Can you hear?
Can you hear us?
Oh, actually, hold on.
I had my speakers.
Oh, okay.
I had my headphones
Can you hear
on.
us now?
Yeah, I have my headphones on. Or I had my headphones plugged in and I didn't even realize.
Okay, I just had a quick question. So
Yeah.
We're finding like the value of the slope, like the numeric value, because they're giving us numbers, but couldn't you just like draw a line with the same slope as C and that's on the same indifference curve as A, and that like would be B?
Yeah, so exactly. I mean, it's hard to pinpoint exactly where that is, but essentially what we're going to do is we're going to get a point and just pretend that this is, that's bad. Pretend that we have a point B that has the exact same slope as point C right here. So this is where point B is. It's just that we use the numbers to be able to like specifically locate where that is.
Okay, got it. Thank you.
And so I had a question about why I set it up like that. I set it up like this particular way because these are two key facts that we're going to need in order to find point B, right? So the way that we find point B is by acknowledging that point B is going to be on the same indifference curve as point A, right? Which we know from this point right here. And we also know that the slope at point B is going to be equal to the slope at point C, which is why I drew a parallel line, right, to this new budget constraint that we have, right? And so basically what I'm saying is that point B is going to be on this indifference curve, and it's going to be tangent to a line that has a slope of 5/2, right? So essentially what we're going to be able to do with this is we find out the relationship between x1 and x2 when the slope is 5/2, right? And we're going to actually be able to plug this in to our utility function. And so what we get right here is that x1, which is equal to 2x2/5 times x2 is going to be equal to 200, right? And so does everybody understand what I just did right here? Right? Can I get some thumbs up or like some thumbs down?
How did you get the 200 again?
So the 200 comes from the utility at point A, right? Because we know what the bundle at point A is, right? We know that the bundle 2010, when you plug that into the utility function, becomes 20 times 10, which is 200, right? And so because of the fact that they're on the same indifference curve, that means that point B has to have the exact same utility, right? But another thing that we know about point B is that the MRS is set equal to 5/2. And so we can actually find out the relationship between x1 and x2 when the slope is 5/2, right? And so given this information that we have, we can actually isolate for a single variable, such as what we did right here. And so this allows us to get basically our utility in terms of x2, right? And from here, it's simply just a matter of algebra. So I'm going to bring this up here. So this is I'm going to use a different marker. And also, I'm sorry that I had you guys essentially muted. I didn't even realize. So we get that 2x2² / 5 is equal to 200, right? So basically x2² is equal to 500, right? So basically 5 times 200 is 1,000 divided by 2 is 500. And so x2 or x2, right? So I'm running out of space. x2 is equal to the square root of 500, right? And basically x1 is going to be 2/5 of that, right? So whatever 2/5 of this is going to be what x1 is. So x1, I'm actually going to erase this if that's all right. So just to give ourselves a little bit more room, that tells us that x1 star is going to be equal to 2/5 of the square root of 500, right? And I'm sure that you can actually simplify this down. I just don't really want to. But let's see. I have my calculator right here. So we can actually get a better idea of what this number is. So square root 500 is roughly 22, right? So this is roughly 22.4. And this right here, because it's 2/5 of that, is roughly 9. So this is roughly 9. And so if you think about where point B is, right, it actually seems pretty accurate that this is, so point B is 9.22, right, just to kind of round. And so if you look at where our hypothetical point B was, right, that's actually very close to where we drew it, right? And this was just a rough drawing that wasn't kind of to scale, but you kind of see how the numbers confirm what the intuition said, right? And so if we use these numbers and we get that, right, we go from point B to point A, right? Because ultimately what we're looking for is the substitution effect for good one, right? We were able to consume 20 units and now we're only consuming 9, right? So we go 9 minus 20, and that's going to be equal to negative 11. So that's going to be the substitution effect for good one. All right. And so this is kind of like, I know that I confused you guys maybe a little bit on Monday just because I only went into it from a conceptual point of view, and it's really helpful when you see numbers. So 9 minus 22 is basically going, so substitution effect is A to B. So going from A to B, that's the substitution effect. And so I subtract my final ending point of x1, right? And I basically subtract that from the beginning, right? How much we started with at the very beginning. And so we originally had 20 units. We went down to 9 units. And so basically the difference between that is negative 11. Okay. Are there any questions about that? I know that this problem maybe took longer than I had anticipated, but I think that it's really key that you guys are understanding what I'm doing to find point B, because point B is really like the hardest part about it, right? Finding point A and point C is pretty easy, in my opinion, but I think that it takes a little bit of manipulation in order to get to point B.
How'd you get x2 equals 500? x2 squared equals.
It's the, so, right, it kind of stems from this equation right here. So this is just a substitute for x1. And so this is the utility function, x1 times x2. And remember, I got x1 is equal to 2/5 x2. And so I basically just multiplied these two together, and I set that equal to 200 because that's the utility at point A, right? And so I know that they're on the same indifference curve. That's why the utility stays the same. And this is just the algebra that kind of leads to x2 squared equal to 500. All right. Does that make sense to you guys? I know that.
I have one question.
Yeah, what's up?
I understood why you set it equal to the utility, and like it seemed pretty easy after that. My question is, we set for finding point B, we set x1 equal to the marginal rate of substitution that we found like in point C.
Yeah, so you set the MRS because we know, right? So going back to like week 1, week 2 stuff, the MRS is just the slope of the indifference curve at any given point. And so we know that this slope has to be the same as this slope, right? So that's why you set it equal to basically the slope at point C.
Right. I understand why we set it equal. My question was, could we then set it to the budget constraint that we used like for point A, like using prices from point A?
So that's actually a really good question. And the reason that we're not able to do this is because when we, right, if you think about this budget constraint right here, right? This point right here is actually surpassing the budget constraint that we were previously on. And so essentially what that means is that because the price increased, right, our purchasing power effectively was changed. And so, right, we're not going to be able to set that equal into our original budget constraint. And I think that that maybe explanation is hard to understand, but
that makes sense. That makes sense.
But basically, essentially, you're not able to do that.
Right, because the budget constraint is parallel to the one from C. That makes sense.
And so Andrew, to answer your question, yeah, it's 11 apples. Okay. Any other last questions about this? I'm going to try to do maybe one more question from this extra problem set. And then I definitely recommend that you guys do this on your own. Okay, it seems like there's no more questions. So I'm going to erase this and we're going to do a different problem. Let me just kind of handpick one. I don't want to go straight to number 2 if it's an easy one. All right, so let's go to extra problem set 4. We're still there. Let's see. Okay, let's do number 3 because I think it kind of encapsulates a lot of what we were just doing, except that it's in a more general way. So we draw our kind of XY graph. So this is X1, this is X2, right? And we're given that good 1 and good 2 are complementary. And so if you remember kind of this email that I sent out to you guys that dealt with like tiebreakers regarding substitution and income effect when the arrows are going in the opposite direction, right? So hopefully you guys remember, which that might be a long shot to kind of ask you guys of, but essentially when a good is complementary to another good, that tells us that, and we're going to say that we're just going to use X1 in this example. That means that demand for X1, when the price of good 2 increases, is going to go down. Meaning that if P2 increases, then I'm actually going to consume less of X1 because I consume them in tandem with each other, right? And similarly, right, it would be X2 and P1, right? So that's essentially what it's saying. And so we would expect that the total effect for an increase in price of good 2 would result in less good 1 as well, okay? And so that's in the Weebly video that I sent you guys. So definitely check that out. But yeah, let's move on to this problem. So using 3 budget lines and 2 downward sloping indifference curve, illustrate the effect of a decrease in P1, right? So P1 decreases. And so because they don't give us any information, we can kind of just draw arbitrary budget constraints. So let's just say that the budget constraint originally looks like this, and I'm going to use a darker marker so you guys can see. So let's say that the budget constraint originally looks like this, and we were originally consuming here, right? And these are kind of just arbitrary indifference curves and arbitrary budget constraints, right? This is like point A, okay? Now, we're given that P1 decreases, meaning that our new budget constraint is going to look something like this, right? Where we get a pivot at X2. And so what we have to think about, right, is, and we can actually draw out this chart. I think that the chart is especially useful in this case. So substitution effect, income effect, and total effect. All right. And so we know that P1 decreases, meaning that, oh, my God, I've been having really bad allergies. I apologize. I was gonna sneeze and I didn't, whatever. So we get that the substitution effect for good 1 is going to be going upwards. And so remember, the substitution is always going to move away from the more expensive good, meaning that it's going to go towards the cheaper good. And so in this case, P1 is now cheaper. And so we move towards it with the substitution effect. And remember that these two arrows are always going to be pointed in different directions. And so that tells us that x1 is going to increase and that x2 is going to decrease through our substitution effect, right? And so that tells us that point B is going to be somewhere on this portion of the indifference curve, right? We also know that because P1 decreases, that's going to mean that the income effect is positive for both goods, right? And so that tells us that the total effect is going to be definitely positive for x1, but we don't quite know what it's going to be for the total effect for good 2. Now, because of the fact that these goods are complements, right, that tells us that when the price of good 1 decreases, then consumption of good 2 is also going to increase, right, because of the fact that they're complementary goods. And so you can kind of think about it in terms of this situation. So right, and that means that if P1 is actually decreasing, then that means that x2 has to be positive, right? There has to be a positive change in x2, right, in order for this to be less than 0, right? And are there any questions about what I mean by that? Yeah, so, okay, yeah, this is question number 3. And so, right, if you think about what it means to be a complementary good, right, which was already established in the question, right, this is the definition right here, right? So x2 is a complement of good 1, meaning that when the price of good 1 goes down, right, so you can think about this as going down, or maybe like a negative sign. So this is negative. Yeah, that doesn't look very good, right? So basically P1 is going in a negative direction. That means that x2, demand for x2 has to be going in a positive direction for this to be a negative number, right? Because if this was negative, so if x2 was actually decreasing as well, that would have meant that a negative over a negative becomes a positive, which would have meant that this is greater than 0, right? And so that tells us that consumption for x2 has to be increasing, which means that the total effect is going to go up, right? And if you remember that slide that I sent in my email on Monday, I believe, when two goods are complements to each other, then the income effect is going to beat the substitution effect, right? Meaning that this arrow is more powerful than this arrow right here, right? And so we're going to get a total effect in which both x1 and x2 increase. And so let's think about what this looks like, right, on our graph that we've drawn right here, right? A point where x1 and x2 increase, so we're finding point C right now, is going to be like right here, for example, right? Where x1 increases and x2 increases. Now, another thing that we want to note is that for the substitution effect, x1 increased, but x2 decreased, which means that a possible location for for point B would be right over here, right? And let's just draw this line right here. And so this is going to complete the problem, right? Where we have it so that each of these points fills out exactly what should occur, right, in this situation. And so that's all I have time for today. I know that I always go over a little bit, but that's just because I want to make sure that you guys all have a pretty good understanding of it. So I definitely do apologize for keeping you guys late, but hopefully it's worth it. Connor, let's see what your question is. So X2 is actually going to have a rising income effect, not because they're complements, but because the price of good 1 went down, right? Which means that we effectively have more purchasing power for both goods, right? Which means that income effect is increased, right, for both goods as well. Is B on the budget constraint or the indifference curve? B is on the same indifference curve as A, but it has the same slope as B. Or C, sorry. All right. Remember, I have office hours, or I guess drop-in hours right after this. So you guys are more than welcome to kind of just hang out and ask me questions. But if you guys don't have anything else, you guys are definitely free to go. Definitely, I would recommend going through the rest of extra problem set 4 because there's a ton of stuff about substitution and income effect and other questions that are going to be really useful to you guys. Yeah, no worries, guys. Thanks, man. All right, let's turn this recording off.